they compare two things, either two groups or two different timing or two different conditions. So that's more of the real world inferential statistics, what we consider as a T family, T statistics family. Okay, but again, until the end of this week, we're gonna look at the foundations of the T statistics. Okay, and if we could, maybe Z table and Z statistics is more robust statistical test because it's more sophisticated. It goes to even in the textbooks of 4 pages long, but T table is just a short 1 page, right? And T statistics was introduced by students like you. Okay, they just try to do some analysis, but there are limitations. So alternatively, they develop t-test. So some of the older statistics, their textbook, it actually said students t-test because a group of students actually developed the t-statistics. Okay, all right, so let's move forward. Okay, so t-statistics, it's still same thing. What we want to see is that whether there is any effect. Like the examples we use, if there's a new medicine, is it gonna be effective or not? So any of those effects might gonna change something in our population of research interest. But the t-test is not the best, but alternatively the best test when we have some limitations, especially we cannot meet the minimum assumptions for the test. Okay, let's go from here. All right, so just let's go back and review again. I ask you guys, do not try to even memorize. It's more of the common sense. So when you do, and in order to do such, like for example, Z test, that is based on the normal distribution, right? We assume that those of data they are gathered, and if we put in the distribution, it's normally distributed, right? So something like that. So Z test, we assume that it's a random sampling, okay? And those samples are not really related to each other. And since we need to fix one, the value as a standard deviation for the population, okay? Just so we assume that across all different cases, the variability is similar, so constant variability, which is standard deviation for the population. We shouldn't know in order to run z-test. And also, z-test use a normal distribution and a corresponding p-value, so we understand that more than 30 cases, the sampling distribution ended up with a normal distribution, so we can use a z-table to find the corresponding p-value. So those are, again, not memorizing, but just to know that's like set of assumptions we have in order to do in a z-test. But here is the thing. When we do z-test, all right, so first of all, of course you have like a set of the sample, so maybe you can get sample mean or proportion, whatever the statistic value you wanted to use. But for example, sample mean, is it something you can get, tangible number you can get. And population value, mostly you can get from the established theory and knowledge out there. So usually we don't have a problem with the numerator of any statistical analysis because that's some tangible number or theoretical number we already know. But most of the statistical analysis, the problem comes from denominator. Based on statistician's decision, denominator is about variability, error, and sample size. So most of the problems comes from like how big the error term is, and whether you have enough or too small or too large. I mean, enough sufficient amount of the sample size, right? So most of the problems and the adjustment should come from the information, whether we have it or not, or the information is valid or not. So mostly about the variability, the error, and also the sample size. Okay. So when we're gonna use a t-test is basically, if you know this, we're pretty much done, but I will go over the details. When you do real world statistics, okay, somehow it can be you know more accessible to get a population mean value and population probability. But most of the time in real world knowledge, we don't have much of information about population, variability, the error term. Okay, so that are often unknown. So beyond the Z statistics, t-test, after test and chi-square test, we all estimate those variability from sample. That is more reliable than any other variability done by an established study. So the real world statistics, we estimate standard error and standard deviation. In other words, the variability of the population using the sample you collected. Okay. So usually when you don't have the population standard deviation and variability, you estimate through the sample. So we use that for the statistical analysis. So all statistical analysis from this moment to the end doesn't matter. It's the intermediate levels of statistics or advanced statistics. We all calculate standard deviations and standard error from the sample. Okay, so we started from now, and also normal distribution table minimum. It seems like it's 30 is not a big deal, but we expect the large enough. The sample size is large enough to not to violate any of those assumptions, but especially let's say students study sorry, my coughing and my undergraduate class, and many students are sick, and I think that there's something going on, and I'm not feeling very well with that. But when, especially the group of students, they ended up with studies less than 30 cases. So what about if we have only 20 cases? We should give up? There's no statistics at all. So a group of students a long time ago, they thought, we do the same statistics. We want to see anything is effective or anything is related. So if we do something with it, the population value will change. So they're asking the same thing, but if we ended up with a small sample size, what are you gonna do? So the group of students collect those statistic value in numerous time and put the probability value to corresponding t statistic value. So created the t distribution table. Okay, the way really conventional z tables work. So in other words, when you use a t-test instead of a z-test, okay, so these are what you're gonna learn from the rest of the semester. So in this situation and this statistic and that and the other statistics or something like that, right? So especially when you don't have information about population variability, number one, and second, when you don't have a sufficient sample size, then you utilize a t-test instead of you utilize a t-distribution table instead of a z-table. You got that? So that's the two conditions. All right. So again, the purpose of the t-test is we compare how your sample doing something and doing different. It might just change things in your population. Okay, so for example, as what we talked about an example, whether new medicine helped the anorexic girl and teenager to gain their weight, for example. Okay, so whether there's a treatment effect or not, if there's anything that affects the population, we're doing things or not doing anything. So the purpose of the test hypothesis is identical between z-test and t-test. All right. So hypothesis is the same. We are, testing the same thing, but we have more limitations doing statistics. Then, especially we have problems with the small sample size, especially when you do not estimate, with you do not really have the population standard deviation, then you estimate from the sample. That's a t-test. Okay. So like this is a z formula, right? Statistics, and we don't know population standard deviation. So what are you gonna do? Rather than just throw away or giving up the test, we use now standard deviation. Here I will go over that notations. It's not universal notations. This is only for our textbook. Some other textbook use different notation, but sigma, middle letter sigma, this is universal notations for population standard deviation. Okay, so sample size and then together, this is a standard error, population of standard error. But in real world statistics, we rarely know population variability. So the better way is to estimate from the sample. So small letter s is a standard deviation of a sample, not the population from of the sample. So that's the information we replace in order to do t-test replacing z-test. Okay, rest of them are the same. They're the same. So there's only additional calculation to come up with standard deviation from the sample. Okay, so just for us, for this class, just stick with the textbook, and sometimes it's small letter s is squared, and some textbook actually they use it as a sum of a squared deviation, and sometimes it's sample variations that they are used as SS. Okay, but again, I don't want you guys to memorize anything. Okay, once you see the formula, you see what what they're talking about. That's the most important thing. All right. So once we just goes back to variability measures we talked about, right? We do not want to have a cancellation problem, so we ended up with the summation of all squared value. It's going to be all positive, right? So we can have some sort of a tangible number rather than zero value for variability. And then it's going to be only increased by sample size. So it's divided by sample size minus 1. That's the sample variance. And then square root of sample size in order to get back to the normal unit and the distance. That's a standard deviation, right? But anything from the sample, we use a small letter s, okay, for the from the textbook and for our further discussion this week, okay? But again, I don't expect you to memorize it, okay? So in order to do t-test, you need to calculate standard deviation of the sample because we don't have that information from population. Any questions so far? Okay, so that's a very common situation that we don't have all information from population. All right. So what I'm saying here is that in reality, we use t-test much more than z-test because the z-test is more of the idealistic form to understand the basic knowledge and the foundations of statistics. But in reality, we use a t-test because most of the time we don't have all information from population, and we oftentimes have a fluctuating numbers of sample size. Right? So now let's move to the okay. So variability we can calculate from sample, and then let's talk about the problems with sample size. sample size, as long as you know any research question or any samples, you have more than 30 cases. Yeah, and although you just use sample standard error, right? So it's a t-test, but actually the probability just pulled out from the z-table because it's a larger sample size. You will have the normal sampling distribution. All right. So as what we discussed, the z-table is only the table with a specific statistic value of z have a specific probability, corresponding to the specific statistic value. But except the z normal distribution table, any other tables, including the t-table and whatever we cover from now on, and any of the statistical analysis, their values, their probability vary by sample size. Okay. Oh, really? Okay, I will show you the graph. I will show you the visualized versions of explanation. So, especially when sample size is larger enough, in this case, if the sample size is closer to 30 and over 30, and Z table and T table shapes and corresponding probabilities are very identical. Okay, but as what we discussed, that group of students had a hard time to have always guarantee at least 30 sample size, 30 cases of a sample size. So what they decide is, what if we have only 5 cases? So what if we only have 7 cases? So that's the t-test. So t-test and the corresponding p-value changes by sample size, especially degrees of freedom. Okay. So degrees of freedom. Let me actually let's explain it here. Degrees of freedom is by definition, right? You can go back to textbook, and from now on, any statistical value will vary by the sample size, right? So degrees of freedom, it comes as a sum of a default value. Any statistical analysis, there are some specific value fixed. Okay, so if set that specific value, rest of the cases in your sample can be free, any value, right? So that's a freedom of degree of freedom, degree of freedom. So for this case, what we need to fix in order to do t-test, especially, we need to fix one value of standard deviation from the sample. So that's the value we fix, but rest of the value can be anything. So simple t-test, the foundation, the basic form of a t-test, the degrees of freedom is sample size minus what you fixed, which is number one, only one, the standard deviation. And the rest of the case can be free. All right. So that's the rough understanding of degrees of freedom. Okay. But just to give you heads up, for example, the extended versions of t-test, especially next week, we're going to talk about t-test for two independent samples. So when you compare, for example, male versus female, and then we're going to fix the male mean and female mean, and we compare. So we fix the two value and rest of the values are free. For the test, that extended versions of the t-test family, the degrees of freedom will be total sample size minus 2, which is mean value for male and female. So that's how you can think about degrees of freedom. All right. So each test and each statistical analysis have a different ways or values of degrees of freedom. Okay. So whenever those statistics dealing with the degrees of freedom, you need to always report that degrees of freedom in your interpretation, in your result, writing up. Okay. Again, as I showed you how you interpret and write up, uh, the result from z-test, I will show you what numbers you need to report for the t-test and how you can interpret it. All right. So just to know degrees of freedom, and sample size is almost identical thing, but each statistics you need to fix some value. So from sample size, subtract the numbers of the values you fix for the test. That's the degree of freedom. Okay. So any values for TF or any like a chi-square value. For Z table, you can use either Z value or P value because it's specific. As long as for example, Z value, uh, you know, higher than 1.96, that means it's far beyond that, usually 0.5, right? That critical region. So we know we can reject the null hypothesis and accept alternative. So we can make a conclusion at the fourth step in hypothesis testing, either based on the statistic value of Z or p-value. But the rest of the statistics, we only need to look at p-value because the statistic value itself, it really vary by different sample size. In other words, by different value of degrees of freedom. Okay, so let me show you what I'm talking about here. Okay, in a minute. So rather than fixing center zero and always it's a standardized one unit as just a unit of the variability. No, forget about it. From now, when you move on to t-test from z-test, which like sometimes people call that the student t-test, it all depends on where and what is your sample size. Okay, what is your sample size? There's no center point. There's no fixed the unit of the standard deviation. So when you read academic journal article, for example, and textbook, as well as in our textbook, when you see estimated z-score means it's a t-test. Right. The alternative way called t-test is estimated z-score. Right. So why you can call that as estimated z-score. Once the sample size is large enough, no more than 30 cases, the z-value and t-values are almost identical. Okay, but still, small sample size, z and t table is quite different. Okay, so that is why you can say it's estimated z-score. And so t distribution, let me come back to this after we see this graph. Actually, this is from the textbook. So let's see, this the short dotted line, the tallest one, is a normal z table, okay, curve, normal distribution. But you see that as the longer dotted line and the solid distribution line, and this is t distribution depending on the sample size, depending on degrees of freedom. As what you see, the differences are their sample size are smaller than 30, and as the sample size gets larger, okay, from 5 to 20, that like convert to closer to the z normal distribution. And as the sample size goes down, as well as the degrees of freedom, as you see the t distribution, it's shorter. And then if you look at the tail side, it's thicker and heavier. Okay, so that means in order to get a certain probability, in order to get to like a 0.5 or 0.05 and 0.01 conventional alpha value, you should go down much further out there to get the probability. Okay, because the error is bigger, so tail is thicker, error is thicker. So that's the differences. You got that? All right. So t distribution tend to be shorter and flatter, like a little fat brother. Okay, cute, right? So that's how you can think about how t distribution look different from z normal distribution. So again, the basic form of a t distribution goes by sample size minus 1. That's the degree of freedom for the simple t-test. Okay? That's where we were. So it is only just determined by the degrees of freedom. Okay. As what I said, the sample size gets larger and larger, especially it gets to at least 30 sample size, case some 30, then it will convert it to almost identical to normal distribution. So especially the data set we are dealing with, it's thousands of cases, right? So they will report the t statistics and corresponding p-value. But the p-value is corresponding almost to z value, z statistics. But we don't say z because we calculate standard error and standard deviation from the sample. So it's a t-test, okay? So that's that meaning of our differences between t distribution and z normal distribution, okay? So any questions so far? Okay. So do not hesitate. Still questions. All right. So as I mentioned that the t distribution so that is why in order to get the same corresponding probability, in order to reject null or accept alternative, you should go further out, to the distribution. So usually t value tend to be larger than z statistic value for the same probability because the tails are thicker, right? Visually, theoretically. All right. So let's actually see how the t distribution and the t distribution table look like. Okay. That is actually on our textbook, page 651, 651. And I collected the image here. Okay, so this is a t distribution. All right. So it looks somewhat different, right? So we talked about one-tailed and two-tailed test. Again, it goes back to hypothesis testing. When you have the hypothesis, it's a directional hypothesis. You already know it's a positive relationship or negative relationship. You can go to by one-tail test. So you need to only measure things for one side of a tail. And it is just about the hypothesis that whether there is effect, whether there is a relationship, but we don't know. We do not want to assume it's a positive or negative relationship or a positive and negative change. Then you can use a two-tail test. So if sept z normal distribution, any other tables, t table, z table, and chi-square table, they actually have really rough lines for, okay, what about when we cut the alpha value of 0.05, okay? So for one tail, 0.05, and two tail, 0.01, or 0.1 and 0.05, and whatever you do, they put like, the corresponding statistic value. So as long as when you have this statistic value, that is bigger than what is the fine line p-value right here, then you can consider that any statistic value gets bigger, they're going toward to the tail side, right? Tail side. So that means that they are in critical region. Okay, so same logics to make statistical hypothesis testing. But here, the thing is that, differences from the normal distribution table and t-distribution table and any other table is actually any other tables beyond the z table. They provide, what is degrees of freedom? So basically your sample size. And then, cutting point, the critical region, whether it's a 0.05 or 0.01, whether it's a two-tail test or one-tail test. So for example, here, let me see. So when we look at the t-distribution, okay, and it is maybe one-tail test, 0 to 5, right? Then the z value is 1.96, but here, that statistic value actually goes by, it's different. It's different by degrees of freedom. So in this case, total sample size I have is just 7, and degrees of freedom, and thus it's n-1 for this basic form of a t-test. It's a 6. So we're gonna go down to a degrees of freedom 6, and then just so I wanna cut here. This is more of the one-tail test I'm looking at, and the tail probability right here, it's gonna be 97.5 means 0.0 to 5, right? The tail probability, 2.5%. So right here, the corresponding t-value is 2.447, right? So this is a t-value. So any of the statistical analysis you done with your sample, and the corresponding, the t-statistic value is larger than 2.447, that means that your your statistic value is in critical region. So you can reject the null and accept the alternative hypothesis that you wanted to confirm. So again, the same logic and procedures for the hypothesis testing. Okay, but here with the t-test, you have just rough line for each statistic value for conventional value 0.01, 0.05, and one tail and two tail. So you fix that value and just make sure your statistic from the sample is bigger or larger than the value. If your statistics you get out of your sample, it is smaller than, for example, 2.447, then it's too high to reject. The probability is too high for null hypothesis. So you cannot reject and you cannot confirm your alternative hypothesis. You get that? Any questions so far? So it's a little bit different way to read the table, but most of the tables beyond the Z table, it just look like a T table, more likely to be look like a T table. Okay, so but is there something interesting you can see if you go to the page 651? That's where this T table is listed, and can you see? You see there where actually that is one page long the distribution table. And can you see when actually that table really ends with the degrees of freedom? They actually cut the table after degrees of freedom 120, right? So anything bigger than, of course, they skip bunch of numbers between. Since they pass 20, 30, right? And they jump to 40 and 60 and 120. So basically, as you see, after they pass the sample size of 30, the probabilities are not much different and the statistical values are not much different. It just can be converted as normal distribution. After that, you can use a z-normal distribution, which is much more sophisticated and precise. You understand? So they cut the total sample size after 120. Just simply go back to normal distribution table. That's how it is. You get that? All right. So T table, since we started with limited information, so no population standard deviation, also sample size is small. So only assumptions we sort of guarantee for the t-test is at least our 7 cases, or 20 cases, at least they are not related. So if you get the samples not from the same family, same household, because in most of the political attitude from same household, it's a strong relationship, right? Correlations. So as long as your sample out of like 7, 8, 9, 10, less than 30, they're independent cases, not related to each other, then that's good enough for t-test. Okay. Since we can guarantee random, really a lot of random representative sample and a sampling distribution table that really guarantee the normal distribution. Since we don't, we at least us try to have at least the population distribution is normal, so it kind of we can use the same shape of normal distribution. It's symmetrical and both sides is identical, but not quite the normal distribution. But if you have a normal population distribution, it look like it resemble like the t distribution. So those are two assumptions we just try to guarantee in order to run t-test. Okay, again, do not memorize it, just think about the logic and why we use it, and that is the minimum. Of course it should be such a small sample size. If your samples are related, it's not representative, but that's basically somewhat common sense, right? Okay, so any questions so far? I know there will be more heavier theoretical explanation here, but starting from next week, it will be more of more weight is applications and how you do it rather than what we are doing. Okay, but still z-test, in order understanding z-test and t-test, that is the basic foundations and understanding logics of any other statistical analysis. So I wanted to make sure I spend sufficient time for you to get the sense. Okay. So as I mentioned, that hypothesis testing is identical. Whatever the test you do, okay. Always the first stage is state the hypothesis, and second stage, just depending on it is your one-tailed hypothesis or two-tailed hypothesis, set your criteria at 0.05 or 0.01. Okay. And then you do statistics. Now we have a z-test and t-test. We have two tests that can run. All right. So you can choose from that. So for example, some exam and some of the questions we can get from the textbook and practice question. Now you can figure it out. Is that the context we should use a z-test? Or is that conditions we sort of compromise to test? So we replace t with z-test and instead we run t-test. So that's some decision you need to make. Okay. So you calculate your statistic value from the sample and then making the final decision whether your statistical analysis, whether it is a z-test or whether it is a t-test, as long as your statistic value from statistics, okay, from your sample, your statistic value is larger than the cutting point from the conventional value of the alpha value 0.05 or 0.01, or your p-value is also beyond, right? So it's smaller than 0.05 and 0.01. So same logic to make the decision. So at this point, I want you guys just look at the page 290. Okay, 290. So let's see some of the the terms that are a little different from so for example, if you go to the page 290, this research question, all right, the number one, actually, I know Grace doesn't have a text, but Rahul or Dylan, would you mind if you read the question number one? I'm not really just doing it, but just I want you guys to see, how the research questions are different. So
And this is page 290?
Yeah, 290, the page number 290, and question number one, learning check question number one. Can you read it for all of us?
Yes. A researcher selects a sample of 16 individuals from a population with a mean of 75 and administers a treatment to the sample. If the research predicts that the treatment will increase scores, then what is the correct statement of the null hypothesis for a directional one-tailed test?
Okay, so that's you already have answers all that, but the difference is okay in the question. It doesn't say it's a normal distribution, right? And also, when you read this question, you should know it's a t-test instead of a z-test. So why? Why you automatically know it's a t-test? So look at the sample size. The sample size is less than 30. Okay, so you do t-tests in place of a z-test. You understand? Okay, so those are the questions that you are getting. So you don't have like a large enough sample size, the minimum at least 30, then it's automatically a t-test instead of a z-test. Okay, also one tail test and two tail tests, each beyond the z normal distribution, they have like a different corresponding the statistic value with the sample size. So all those tests you need to look at. If it is not really awesome, it's a normal distribution, but with a small sample size, it is t-test. So I do not want to do that in the class, but just to do some, especially Dylan and Robert, and just there's an answer already, and just try to answer some of those, practice those questions, and so you can get a sense of why we are, doing. And this is the context when we do t-test in place of the z-test. So it's not only now, it's whether it's kind of a debate between whether you have that information, all information from the population, or whether you have a large sample size or not. So that's some of those criteria, whether you're going to use a z-test versus a t-test. But starting from next week, there are much dynamic that is not only the given information, but at the same time, the context of information. What you're measuring, that is additional information, which test you're gonna just, move along and, just flow with. So that will be the practice we will do and, every week and additional week moving along. All right. So hypothesis testing wise, what I'm saying here is that identical. All right. Just making sure your statistic value and p-value is a critical reason or not. As long as in the critical region with a small p-value and larger statistic value, you can reject the null and accept alternative. So in other words, you can say it is statistically significant that medicine have effect. Okay, medicine has effect or not. Okay, so here I wanted to introduce new effect size measure. Okay, I don't know whether you remember from last week. I'm not a big fan of quantity. Okay, because many sociologists, it's more of the like a statistic values, a okay, just go back to the history. The sort of a father of empirical sociology, right? So there are a couple of, especially some of early quantitative sociologists. They decided to use quantity once they done any sort of analysis. Right? So that is based on any of the statistic value you are measuring as a numerator, and then any of the standard error, okay, especially standard variability. I'm sorry, I want to take it back. In variability, especially standard deviation as a denominator. And I was just thinking that that is larger than 0.2, that statistics is good enough. It has a significant effect size. So that's what they start to use. So it's very common in sociology studies. They use the quantity. But as I mentioned that, the reason I do not like it that much, once you're done, like look at the Z formula. It's a mean differences between sample and population and divided by standard error. So basically, once you did the Z test, why you need to do quantity. But I like R square as effect size. And also, it provides a pretty much intuitive and informative information beyond what you done with the test. So when you done t-test, okay, so you found that, okay, it is statistically significant, you already have a t-value right there. So with the t-value, especially t-value, squared, divided by, do not memorize it, okay? Whatever you do, you have a formula in front of you. So, or statistical software will calculate that for you. And then divided by square the t-value plus degrees of freedom. So that's our square value. So as long as you know t statistic value, you can calculate our square value. It will be much more straightforward and significant when we learn regression model, okay, multiple regression model and simple regression model, because we're gonna use our square value to understand. Okay, so your independent variable, how much it explain your dependent variables. Okay, but you try to explain the tendency of a political polarization by knowing like your partisanship and your ideology together, how much that explain. So R square value in intuitive way, in interpretation, it really represent the percentage of the changes and variations explained by whatever you're measuring. So in this case, in today's example, simple, maybe too simple. So whatever you do in your population of your research interest. So that, for example, the medicine, let's say your R square value ended up with a 0.02, it explained 1.2% of the changes in the total population. That's what you can argue. So because of that more informative ways of the effect size by percentage of explanation, I like R square, okay? But what I'm saying here is that R square value will come up again as main key values for the regression model and different, expanded models of the regression and related to correlation and also a multiple regression and different types of regression models. So it will be much more intuitive once we get there. But now just understand, once you know t value, you can come up with R square value. That means it explains that medicine explain the percentage of the changes in the population. Okay, so this is the second measure that we cover as the effect size that I like better than on the quantity. Okay, so when you write up, okay, so we'll do this on a Thursday, actually running some numbers in SPSS, okay? But when you have, okay, like the other day, Grace asked me, okay, we have these tables from SPSS. Is that the right way to do? So most of the time, and our textbook is relatively doing better job, but most of the statistic book, they don't explain what you're gonna write up. how you're going to write up with the statistic result. Okay, so these are the numbers you need to report for the t-test. Okay, so t-test means you just kind of compare something, especially basic form of a t-test. So we compare something between our sample statistics and as as the basic as the population value. So you report t statistic value here. And again, you can say p-value equals as what statistics is report, okay? Or you can simply say at least the message is that your p-value is smaller than conventional value of alpha of 0.05 or 0.01. It's just smaller than that. That's the only thing we need to know, right? And then now you have a t-value, so you can calculate r-square value. So together, you can cut it here. You without r-square value, nobody gonna point in, you are wrong. But you need to provide, by the way, the degrees of freedom for t-test. Why? Because the t-value vary by the sample size, right? T-value is so important because the sample size is 16. We know that it's not z-test. It should be t-test, right? So degrees of freedom is always the necessary information for your readers or your audience to understand why you use a t-test, especially if it is a small sample size. So report the degrees of freedom. In this case, maybe 15 for the sample size for 16, or 6 for the sample size 7, right? So t-value and degrees of freedom. And APA style and MLA style, sometimes they have the round bracket and square bracket. I don't care, but just depending on your style in your paper. But p-value and r-square value. So here, when we say r-square value 0.3 means, for example, whatever you do for the medicine or anything you just had it done in the experimental studies or changes, it explains about 30% of changes in your population. This is the number you can use for that interpretation. Okay, so since for example, we use the alpha value of 0.05, we confirm that the p-value is smaller than alpha value. So regardless, so whatever you ask for, statistics software, they will know. They always test null hypothesis. So their probability is too small. So we can reject null hypothesis. Instead, you can confirm or accept your alternative hypothesis. Okay, so that is a more statistical way to say it. But most of academic journal articles, quantitative journal articles, they say that, yeah, we failed to reject or, we confirm the hypothesis, and you can say that. But regardless, once you fail to reject the null hypothesis, so you cannot confirm your alternative hypothesis, you can say it is statistically insignificant. So what is insignificant? The medicine didn't work, okay? Or then you really confirmed and happy end. So you successfully, reject the null and accept the alternative hypothesis. That means what we oftentimes hear from academic work, it was statistically significant that medicine worked for the population. Okay, so you can state the alternative hypothesis after it is statistically significant or insignificant, following that. All right. So that is how you're gonna write out your result with the t statistic value, mostly identical with the z statistic value, but additional value you're gonna report is the degrees of freedom for t-test and r-square value. Okay. Any questions so far? Any questions so far? Okay, so I think I will. Yeah, let's actually. I know it's just more theory based, so I'm sure you are a little bit bored. But let's talk about in our interval estimator. Okay, it will be shorter and brief, and also Thursday class we can just all play with SPSS. Okay, I can stop here and let you go, Lee. May I need about 15 additional time? Okay, so I can cover this one on Thursday, or Dylan, Rahul, do you want to finish class a little early today and to do your assignment, or what do you want? Depending on you want to keep going? Then
I'm okay with either. But I do need one more source for my 14 sources. So I don't know.
Okay.
We could class early. I'm okay with that.
Okay. I know, Rahul. What about you? Also need to fill it in few resources, right?
Yes, yes.
Okay. Okay. So then, yeah, it's a little bit like a different dimensions of the explanation. So rather than like a kind of overlapping with what we discussed today, I will stop here. Okay, I will stop here. And then Thursday, you're back in fresher mind. We're gonna talk about confidence interval. So that's another the statistic value we use for statistical analysis that any other statistical analysis can really provide. It's just not with specific p-values, possibly, but with the interval, also we can confirm statistical significance. So I will cover that, on beginning of a Thursday, maybe 15 minutes, and then we're gonna move on the SPSS, play with the real data, just to test and practice a t-test. So okay, I understand that I gave you some flexibility. So go for it and do your assignment that is due midnight tonight. All right. So I will see you on Thursday then. Okay. Thank you for great attention. I really enjoyed the class. And before you go, any question, by the way, regarding what we covered today? Okay. All right. Then have a good afternoon. Enjoy your assignment.
Awesome. Thank you.
Okay. Bye.
Thank you very much.
Thank you. Thank you. Bye.